In many experiments, the goal of the experiment is to optimize a specific method or a specific function. So today we are going to be discussing one special type of optimization that we call the simplex method. First, we will introduce the concepts of optimization. We will define objective functions, which are important to define the criteria for optimization, and then specifically talk about the simplex method, which will be relevant to experiment 4. This is a reference where some basic principles of simplex method could also be found. So let's begin then by thinking about when is optimization required or needed in analytical chemistry. And we can think of experiments that many of us have done in which we needed to optimize the wavelength to measure the absorption of an analyte. For instance, in experiment 1, we were finding a wavelength to measure the absorption of methylene blue. We can also think about when we are doing a separation by chromatography to try to understand how we can actually have very sharp peaks by optimizing the number of theoretical plates in the chromatographic separation. Or we can think about, like in experiment 4, try to optimize the emission intensity of a fluorescent measurement. So all of these type of measurements then will require to have a specific procedure to find the best condition for the measurement in question. And this is what we define an objective function. For example, we can think of, as we mentioned before, finding and optimizing the maximum wavelength of absorption, or the theoretical plates so that the separations are effective, or the sensitivity of a calibration curve, or the limit of detection of a measurement or a method, or the recovery of an analyte from a complex matrix, or the time that it takes to complete the analysis. All of these are continuous quantities because it could be any value in a given set or range. In some other instances, we might want to optimize the parameter that is more discrete in nature. For instance, if we are isolating a chemical compound for the first time, we may want to decrease the number of cleanup steps. Or if we are trying to detect as many compounds as possible in a separation, say by gas chromatography, we might want to maximize the number of detected compounds. So objective functions then have a goal in mind. It could be minimizing or shortening or maximizing or lengthening a specific process. In this particular mini lecture, we are going to talk about continuous quantities. And for that, the simplex method is an ideal method to conduct this type of measurements. So let's talk a little bit about what the simplex method is all about. The simplex method is really a method that is based on sequential approximations. What that means is that we are going to try to guess in a logical manner what are the best conditions to complete a given measurement or to find the optimal conditions. So what we will do then is we'll follow these following steps. First, we will need to define the objective function. As we mentioned before, it could be any of the parameters such as theoretical plates. It could be as well the maximum absorption, could be a limit of detection, etc. We will define the optimization, which could be a maximum or a minimum. And we have to define a convergence criteria. This is particularly important because we want to know when we need to stop this optimization process. We will need to define the number of parameters or dimensions to optimize, and we will call this K. For instance, if we have 2 reagents required to give a specific product, the amount of each reagent might be important to consider. Then we will conduct K+1 measurements. Once we have conducted these initial measurements, we will have to select among those measurements the best response, the next to best response, and the worst response of these 3 measurements based on the criteria that we described above. Once we have done that, then we will need to start preparing for the next measurement. What is the next measurement that we need to do based on the best, next best, and the worst response? We will then reassign the best, next to best, and worst response, and then we'll repeat the steps until we find the conversions. Of course, this is a lot of words that don't mean anything at this point in time, so why don't we try to do an example, a more specific example? And one way that I like explaining this is by looking at a graphical representation of what this might entail. So let's begin then by imagining a reaction that requires vanadium, and vanadium is going to form a complex that is visible, that absorbs light in the visible range at 554 nanometers. This complex is represented right here. And we can also imagine as well that this is going to have a structure that is going to be similar to something like that. So what we would like to do then is figure out what could be the best conditions to maximize the absorbance of this compound. Two reagents are important in this case. One of them is going to be hydrogen peroxide, and we can imagine that in order to, for a fixed amount of vanadium, we want to add certain number of drops of hydrogen peroxide, and we also would like to add certain number of drops of sulfuric acid. And the optimized procedure would be such that for a given number of drops of these two reagents, we should have a maximum absorption for this compound. So in this particular situation, we have two parameters, or k equals 2, that we want to optimize, or we want to find for the optimization. So that means that we're going to have to start with k plus 1 measurements, which basically means that we are going to be doing 3 measurements as the initial step of the simplex method. Once we do those 3 measurements, we are going to assign the best, the next to best, and the worst combination of measurements. So let's imagine then that we started by, given by the instructor or the TA, or by just proper consultation with the literature, with 3 combinations of certain number of drops of hydrogen, of sulfuric acid, defined by these 2 axes here. Here is another combination that we followed, and here is the third combination that we followed. And what we can see then is that when we have these 3 combinations and do measurements of absorbance, we will have the best response when we have this combination here. We're going to call this B0 or initial. The next to best response was obtained with this combination, and the worst response was obtained with this combination that we have here. So with these 3 measurements, the procedure implies that we have to try to guess what would be the best condition for this. What is the next measurement that we need to do? So what we're going to be doing then is to try to imagine that in a system like this, we want to really stay away of the worst, from the worst conditions. So the tendency will be then to move away from that and try to be as far as possible, but within reason, from that. So what we do in terms of the visual representation here is that we are going to use this plane between the best and the next to best, and try to project the worst condition to the other side. And we are going to define a new point here. This point we are going to call it for now R. And if we were going to be measuring that particular condition, we will have to have a new number of drops of hydrogen peroxide and a new number of drops of sulfuric acid. So the idea then is that based on this prediction, we can now take a measurement and determine if the absorbance is better or in fact has not improved as much. So this corresponds to the beginning of the prediction, what should be the next measurement. So how are we going to do that? Well, when we do that then, we can basically do that mathematically. We call this process that we just described a reflection. And what we do to do the reflection, we are going to have to calculate a point that is the half point between the best and the next to best. And this half point, we're going to call it the centroid, or P. And of course, that centroid represents a given number of drops of the two reagents that we have in mind. So the reflection, or point R, is calculated by taking the value of P, the coordinates of P, the X and the Y, and then adding the distance between the value of P, X and Y, from the worst point, the coordinates X and Y of the worst point. So even though this is a generic expression, it represents the same process that we had here, which was basically moving away from the worst and going towards the R. So mathematically then, one can imagine that if we know what the initial values of B, N, and W, we can predict what should be the new measurement of R, or the point R here. So that's good. But now what do we do next? What we need to do next is to try to understand how we're going to use the result from that R value to do the next measurement. So let's assume there that we have now the R value determined. And when we do the measurement of absorbance at that particular number of drops of the two reagents, the possibilities of that measurement could be that it's going to be better than the initial value, the best value that we already had, that it's going to be in between the next to best and the worst, somewhere over here, or that it's going to be somewhere in between the best and the next to best, so somewhere over here. Or it could be that it's going to be worse than both the next to best and the worst. That means that it might be found somewhere over here. So depending on what the result of that measurement is, then we're going to have to make a decision. So let's take case by case to figure out what decision we need to make. So let's focus on when it's better than the best initial measurement. That really means that we really would like to move away from that, move in the direction of the best. So what we will do then is that we are going to take the measurement of R, and now we're going to go even farther away from the worst until we get to this new point here. So this new point is going to be important to us because it will allow us to be able to calculate the particular conditions that we have here. So this is going to be called an expansion, or point E. And again, that happens when the measurement at R is better than the best. So what we can say now is that once we do the measurement, we're going to be able to decide whether with this R point here that we just did, we can say then that this R point, it was best. So now this R point is the new best that we have. The next to best is going to be the best that we had before, B naught. And the worst point now is the next that we initially had here. So that's one possibility. But what happens, let's think about case 2. What happens when the results of this measurement, the R measurement, is between the next to best and the worst to best? What can we do in that particular case? We know that in this particular case, we want to be away from the worst, but we know that it's going to be somewhere over here. So what we could potentially do is basically do an expansion towards R, but not as far. So we are going to select this new point here. And this new point here is going to basically help us predict it's going to be the next measurement that we are going to be doing here. So that means then that in this particular case, the R that the best measurement that we did in this particular case is still this initial one. The next to best that we did is still going to be the N naught, and the worst measurement that we had now is going to be the R. And again, we are going to basically define this point that we have here as CR. Okay? It's a partial expansion towards the R direction. So now let's go to the next condition. Let's imagine that we have we did the R measurement, or the measurement at at the R point, and now we have the absorbance that we read is going to be between the best and the next to best. So we still would like to have a selection of a point in this particular region. So what we are going to be doing as well then is that we know that in this particular case, we are going to have a best as the best condition still. The next to best is going to be, we don't really know what it is, but it's very likely to be the R, and the worst is going to be the N naught again. And the measurement that we are going to be doing is going to be localized right here. We call it CR again. The last option, option number 4, is when the value of R is worse than the next to best and the worst. So that really means that this value, we have to move away from this value, and we're going to try to go towards the opposite direction. So this is going to be what we're going to call the CW point. Now, in this particular situation then, the original best condition is still the best. The next to best is still the best, is the second, still the same as next to best, and R now is the worst, and that's why we move to this particular CW position. So now the question is, we are doing this visually. Can we do this mathematically? And the answer is yes. We can basically write expressions for each of these cases that will allow us to represent these particular conditions. So let's go back then and rewrite for each of these conditions what the expression would be. So let's begin then by looking at the calculation of R. For R, the calculation that we will be using is going to be, as we described before, the centroid or P plus the difference between P and the worst. We are going to define for E the expansion, a similar expression, centroid plus 2 times P minus W. We are doubling the direction or moving away from the worst. Now, if we are going to do a partial expansion, the expression that we will use for that will be the centroid plus half the distance between P and W. And the same thing will apply for this one here. CR is going to be equal to the centroid plus half P minus W. And lastly, for the contraction, the new point is going to be P minus half BW. So these expressions, these mathematical expressions, could be easily worked out if we use an Excel spreadsheet. For example, we can use an Excel table to illustrate how to use Simplex. So in this table we have the initial setup for the Simplex method. We have the 3 initial measurements, 1, 2, and 3. The 2 parameters that were mentioned, which are the drops of the 2 reagents, reagent 1 and reagent 2. And for each of these ones, we are going to have a signal that was measured. Since in this example we had 2 parameters, so k equals 2, the number of initial measurements that need to be made is going to be k plus 1 equals 3. So these 3 measurements gave the readings 51.9, 62.3, and 67.5. These are absorbance readings, as we mentioned before. We also want to maximize the absorbance. So we know that the best measurement is the one corresponding to vertex 3. The next to best is vertex 2. And the worst was vertex 1. In the initial setup of the Simplex table then, what we will be needing to do is to calculate the parameters that were defined previously. So first, let's focus on the centroid. And the centroid, as we said, is basically the average of the coordinates of the 2 forms that we have here. So if we take the average of x1 for the next and best measurements, we can then obtain an average corresponding to 5.5. For x2, the average would be 16. We also need to calculate the position of R. And using this formula, we can see that we have to take the centroid and the difference between the centroid and the worst measurement. So for the x1, that will give a total of minus 14. And for x2, gives a total of minus 1. If we do a reality check, we know that x1 and x2 represents drops of solutions A and B, the 2 reagents that are part of this particular analytical example. So what we would like to do is to adjust that to something that is real. So in other words, we have some restrictions or boundary conditions. In this particular situation, the boundary conditions is that we have to have a number that is going to be greater or equal to 1. So we are going to adjust R to make it R prime, and we are going to take the values as 1. We are rounding up to the boundary condition. So now let's assume that we take a measurement when we use 1 drop of A and 1 drop of B. And we observe a reading of 40. So this is still part of the initial setup. What we need to do next is decide where our next measurement for the next iteration will be. So what we can do then is that based on this particular situation, we will compare the measurement of R prime, which is 40, with the other ones, and we basically decide where it lies. What we can see here is that 40 is worse than any of the other measurements that we had. So we are going to because of that and because of what we discussed before, this corresponds to a situation in which we are going to have worse than the next best and the worst, which will basically mean that we are going to have a contraction. So the activity that we'll be doing here is a contraction, which before was called case 4. And the calculation of the new conditions to measure correspond to CW. We will need to calculate CW using the values of P and P minus W. And when we do that, we obtain as a new result 15.25 and 24.5. Clearly, we need to measure drops, and we are not going to be considering numbers that are not integer here. So we can round up that CW to 16 and to 24. So the ideal situation would be then that if we want to continue, this finishes the first or initial setup of the simplex. Now the ideal situation would be to take these numbers and do a second iteration. So if we are using Excel, we can create another table, and in this new iteration, what we are going to be doing then is to consider the values that we had from the previous table and the new value that we calculated from the contraction. So as we can see here, this corresponds to 16 and 24. And if we are going to measure the signal, for instance, 55, at that particular value, we can keep then the previous value of N1 and the previous value of P1. So we can repeat the process again and again until we finally get or reach convergence, depending on the criterion that we define. And you can optimize and automate this using Excel so that eventually we have conditions. It's hard to believe, but if we do it this way, it's going to be way simpler than trying to have a multitude of measurements done in a more systematic fashion. And this is the utility of the simplex method, optimization by finding a sequential and logical procedure of the best conditions.